Alright guys, today you learned one of Newton's laws. I don't remember if I told you which one it was or not, but it wasn't the first law, so we've done things a little bit out of order. We actually learned Newton's second law. F equals ma, a equals f divided by m, whichever way I told it to you. I'm recording this before I do that lesson, so I don't know. Now, the first law is actually the exact same thing. Just instead of being mathematical, it's just an explanation. So Newton's first law says that objects don't like to change their motion. They have a tendency to keep doing exactly what they're already doing, either sitting at rest or moving at a constant speed, which, if it didn't do those things, it would be accelerating, which would mean there would need to be a force. So the way you've probably heard this before is that objects in motion stay in motion unless acted upon by an outside unbalanced force. That's the whole spiel that we give, usually for Newton's first law. But really what it boils down to is inertia. Things like to keep doing what they're doing. So, that has two real implications. The first one is that, well, exactly how it sounds. If there's nothing to stop an object from moving, it won't stop moving. So, by the same token, if there's nothing to start an object moving, it won't start moving. So, I have two objects here. The case for my speakers, and a disc for one of my games. Doesn't matter. So, these two things, with no forces acting on them, won't do anything. Of course, there's forces acting on things all the time. Right now, there's gravity acting on this object. The reason it does not start accelerating from that gravitational force is that my hands supply a balancing force. Note that, remember, Newton's first law said it had to be an unbalanced force to start moving. Or, looking at F equals ma, if F is 0, then so is a. That's how math works. Since I balance out the force of gravity, the total force ends up being 0, so nothing moves. Just sits here. So, now, I'm only actually going to apply force to the bottom case, and yet, the top case will move with it. So, since I didn't apply any force to the top case, why does it start moving? It has to have an unbalanced force acting on it in order for it to start moving. Where's the force? That's going to be our old pal friction. There is friction between both of these two surfaces. Makes sound when you rub them together. If you did it long enough, it would heat up. You would notice it. There's something that's actually a contact force going on between these two things. So, as long as that friction force is doing its job, then if I move the bottom part around, the top will move with it. Unless I do it a little bit too dramatically. So, as long as I hold it in place, then there's a balanced force that causes all of the stuff to move together, even when I do it quickly. Nothing happens. However, if I release the restraint on that top part, and then start them moving, if I suddenly stop the bottom part, but I don't do anything to the top part, there should not be any forces that are stopping it from wanting to keep doing what it's doing, moving at a constant speed. So, if I only stop this, and I don't put any forces on the top, it's going to try to just keep going, just like it did. They're moving together. I stop the bottom. If I do it slow, the friction does its job, and stops the top part as well. But if I do it too quickly, friction isn't strong enough, and inertia takes over. That object in motion stays in motion. Now, the other part of inertia is that larger objects have more inertia. Inertia is a property of an object. Usually, we call it mass. Mass and inertia are actually the same thing. They are a measurement of that tendency of an object to not change motion. So, for example, let's go back to our old equation. Whoops, I need to shrink my face. So, our equation over here, a equals f divided by m. I've rearranged it. I just took the m, divided it over with the f. So, the acceleration is the force divided by the mass. That's the mathematical form we've already seen. The thing that we're talking about with inertia says bigger things are harder to change their motion, harder to accelerate, harder to get the same amount of acceleration. So, just for an example, let's say you put the same amount of force on two objects. One of them is large, and one of them is small. So 50, whoops, that's not my drawing tool. 50. Let's say we put a force of 50 newtons on an object. The acceleration that it experiences is going to depend on that mass. So 50 divided by a large number, like, I don't know, another 50. So a 50 newton force on a 50 kilogram object is only going to give you an acceleration of 50 divided by 50, which equals 1. 1 is not a very large acceleration. Remember, gravity already is 9.8, and I told you gravity was the weakest force. So that is barely any acceleration at all. So, and the 50 and 50 thing, it's just to make the math simple. So a 50 newton force also isn't that big. But you understand the point. With the same amount of force and this amount of mass, we get an acceleration of 1. However, if I put that same 50 newton force on something that only weighs like 5 pounds, well, now we got a whole different ballgame. 50 divided by 5 is 10. Now we've got something more comparable to gravity. So that smaller object that only weighs 5 kilograms, from the same amount of force, experiences a much higher acceleration. It can speed up or slow down much faster with the same amount of force because it doesn't have as much inertia. It doesn't have the same level of resistance to change. So, as an example of this, think about our traffic light at the bottom of Bardstown Lake. Bottom of that hill, right, going towards Fern Creek. So, before that traffic light, there's another set of caution lights farther up the hill. Why are they there? What do they do? Why is it necessary that somebody need to know before the traffic light turns red that it's going to turn red? Let me give you a little bit of a hint. Think about, say, a larger car. Maybe not even a car. Let's say it's a semi. And let's say it's raining. The worst possible conditions. So, the rain notwithstanding, that's going to reduce the friction force and make everybody harder to stop. The semi has another problem. It's very massive. It has a lot of inertia. So, let's assume they don't, but let's assume for a second that a small car and a semi can experience the exact same braking force. Let's say that it's 50. Let's go back to that example. That semi, the larger car, with the same braking force of 50, that larger 50 newton, 50 kilogram truck, it's a 50 kilogram truck, don't worry about it. It's a large value, which only gives you a small acceleration, whereas a smaller car, a 5 kilogram car, has a much higher acceleration. So that truck needs a whole lot more space in order to stop moving. I think my face is over on the side, but that's okay, you can hear the point. So, yeah, objects that are litter take longer to stop or start, doesn't matter. Hello. Anything that's in motion tries to stay in motion. Bigger things have a bigger resistance to that change. Remember that.